All right, well, I want to talk about the limit definition of the derivative, but I want to talk about it versus derivative rules. Well, what do I mean by this? Well, I mean there are two basic ways, two main ways that we can evaluate derivatives. We can plug things into the limit definition, or we can use derivative rules. One is always more labor-intensive than the other. I say always, it's probably almost always, but I'm hard-pressed to think of a single example in which limit definition of the derivative is going to be less work than just using derivative rules, and I think you'll really see what I mean here. So let's talk about this. This is a problem that you see here, f of x, this function, f of x equals 1/2 x minus 3/5. This is a pretty simple, rational first-degree rational polynomial function, and its derivative is very easy to take, but I've made a video previously, and perhaps you've watched it, it should show up earlier in this playlist, this derivatives or differentiation playlist on my channel, and I use the limit definition of the derivative to differentiate this function, and it's shown here. I'll explain that in a minute. So the limit definition of the derivative states that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And h, we can just think of h as being equivalent to delta x, or the change in x. So what are we doing here? Well, we did the limit definition of the derivative, and we said, okay, limit of h approaches 0 of, well, 1/2 x plus h minus 3 over 5 minus 1/2 x minus 3 over 5 equals the limit as h approaches 0 of 1/2 x plus 1/2 h minus 3/5 minus 1/2 x plus 3/5. So we were able to cancel a whole bunch of terms, as you can see by the, is denoted by the blue markings there, the mark-throughs. With the limits, we took that and so we canceled terms, which is this is now equal to the limit as h approaches 0 of 1/2 h over h. The h is canceled, so it was just the limit as h approaches 0 of 1/2, and that was just 1/2. Whew. Now, I go through and I say every single step to that, and I read every bit of that problem, not just to torture you or waste time, but to illustrate a point. It's labor-intensive. It's not hard algebra, but man, it's a lot of algebra, and if you need a derivative on the fly, this is really going to take a long time. So what's the point of using the limit definition here? Well, it's a terrible idea to use the limit definition of the derivative on this problem. It's much easier to use derivative rules. I can look at this problem and in 1/10 of a second say, oh, well, the derivative, that's 1/2. I don't even have to think about it. And if you know derivative rules, you won't have to think about it either. It's extremely, extremely simple. Here's why. Let's think about this function. Our function is f of x equals 1/2 x minus 3 over 5. So let's rewrite it here. We have f of x equals 1/2 x minus 3/5. Okay, cool. Simple function. Let's start thinking about derivative rules. If you haven't seen my video on derivative rules, I have one, and I explain all the basic derivative rules that we need to talk about. I don't delve into the chain rule, and we don't need the chain rule for this either. So that will be in a different video. So if you go watch that and wonder where that is, it's not a basic rule. So I wanted to save it for its own video. So let's talk about some basic derivative rules here. Well, I think the number one easiest one to look at is the constant rule that says any constant prime is always 0. And well, this is pretty simple. Why this is the case? Think about a graph, and I'm going to graph like x equals 2 or something on it. Well, what's the slope of this? Is it ever going up or down? No, of course it's not. It's never going up or down or anything like that. So the slope is just 0. M equals 0. So if m equals 0, then f prime is also going to equal 0. So that's all this means, and that's why that makes sense. So the c prime is always 0, right? So let's go ahead and let's write that down. C prime equals 0. Maybe if we actually made that look like a c. C prime equals 0. So if c prime equals 0, do we have any constants in this function? Well, yeah, we do actually. Negative 3/5, that's a constant, right? So it's equal to 0, so we don't even have to worry about it. It's gone. It no longer exists. Now, think about another derivative rule. Well, a constant times a function prime is just equal to the constant, and I say constant times function, all of that bracketed prime. If you're just listening to the audio here, it's c times f, those things within parentheses prime, is equal to the constant times the function alone prime. So that means that if I have something times a variable, then it's just that thing times the prime of that variable, right? So I've got something times the variable here. I've got 1/2 times the variable. Well, I've got x, so that means it's going to be times the variable prime. Well, x prime, oh wait, that's also one of our derivative rules. X prime is always equal to 1, right? So with these three rules, we don't even have to use any other derivative rules except that. It's x prime equals 1, so c times f prime would be 1/2 times 1, right? So since we're multiplying here, 1 is not changing anything at all, so let's just get rid of the x. We don't care about it either. So now we've determined, just on these rules, that f prime of x is equal to 1/2. So if you know these rules in your head, you can look at a function like this. You can come see the function f of x equals, was it 3/5? No, 1/2. I'm sorry. 1/2 x minus 3/5. You can see a function like that, and you can say, okay, constant doesn't matter, multiplying by 1 doesn't matter, derivative is 1/2. Now, tell me, I don't know about you, but those 2 seconds of work sure are a lot easier, and there's a lot less room for error than all of this stuff right here. This is just a pain, right? So why would I want to do that if I can do this? This is a lot easier, I think, and this is the way to go. So that's all there is to this.